Okay, a very good afternoon. Actually, myself, Srijan Sengupta. I'm an assistant professor in the Department of Metallurgical Materials Engineering, IIT Jodhpur. So I work on battery materials mostly and electrochemistry based on corrosion. So I'm going to give a small talk on SN, that means steam-based anodes for lithium-ion batteries, and some batteries which are beyond lithium chemistry. So I start with a very fundamental and go to a little depth. So if you see in the first hand side and the left hand side, so it's just a piece of zinc dipped to and concentrated HCl. So zinc is dissoluting and there is an evolution of hydrogen gas which is taking place. So if you see the reaction, which is oxidation of zinc and nothing but the reduction of hydrogen. But where is that both the reaction is taking place? The reaction is taking place on zinc substrate itself. So zinc itself is acting as an anode and itself acting as the cathode. Okay. But the same arrangement, what you do if you just put a galvanic couple in that same HCl where zinc and copper are coupled together, there also you will find the same reactions are going. That is, zinc is oxidizing and hydrogen is reducing. But in this case, zinc becomes the anode, which was in the previous case, but copper becomes the cathode. Why? Because in this case, copper does not react with the solution since it is not that much electropositive, but it provides the surface for hydrogen reduction. So hydrogen reduction mostly happens in the copper substrate. So what is different from the earlier case is that the electronic transport, which was confined into zinc, okay, is not confined into zinc anymore. So the electrons are transported from zinc to copper in order to complete the redox reaction. So we are able to trap those electrons and we can put it to a load, and this corrosion reaction, this modified corrosion reaction turns into a battery. So this battery is nothing but a corrosion reaction in which the electrons has been separated. The anode and cathodes have been separated. It is very important to know this because all the batteries that we have, when we go for the degradation mechanism of all the batteries, we will see that it's mostly corrosion reaction which degrades those batteries. Okay, so this was actually the most primitive form of cell that we used to have, which called the voltaic cell. And the basic parameters of these batteries is voltage, capacity, and current. So if we come one by one, the voltage can easily be found by the help of something called the reduction potential table. In this, they're organized in the form of their redox reactions, and something on the top will act as a cathode, something on the bottom will act as an anode. So if you just get the zinc oxidation and hydrogen reduction reaction, we'll get a voltage around 0.76, which is a difference of these two. And if you come to the capacity is nothing but the charge that you can store in a battery. So that charge generally is told in form of milliampere hour per gram. So we talk in terms of specific capacity, not the ideal capacity. Specific means per mass how much it can store, or per cc what it can store. So if you just see this reaction, zinc oxidation and hydrogen proton reduction, so it actually involves a charge of 2 mole of electron, which is 2 farad. And when you convert to milliampere hour, it becomes 53611 milliampere hour. And if you consider the entire mass, it is a mass of 1 mole zinc plus mass of 2 proton, which is the 2 hydrogen atom. So this is total 67.3. And if you just divide by that, you will get something around 800 ampere hour per kg capacity or specific capacity from this very primitive cell. And you know that electrical energy is nothing but the charge multiplied by the voltage. So if you do that, you come up with something called 0.65 kilowatt hour per kg. So this is the amount of energy you can get out of this primitive cell. Now, just for comparison, if you compare with that of gasoline gives us something around 47.5 millijoule per kg, that is 13.2 kilowatt hour per kg. So it is almost 20 times better in terms of capacity or specific capacity with respect to that of this primitive battery. So that is, we have to see how to improve this battery chemistry, that we can go as close as possible to the gasoline energy if we have to actually replace them with the batteries. Now, the third parameter that the battery should have, that is the current, or that is the power rate. So power of a battery is nothing but the voltage multiplied by the current. The voltage you have already done with, but the current, if you see for this primitive battery, the current is very low. The reason for current is very low because you are producing a gas H2, which is an insulator. So it will keep on attaching to the surface of this copper and keep on reducing your area. So much less area will actually contribute to your electrochemical reaction. You will get very less power. And on top of that, that hydrogen proton has to reduce. It has to form H2 molecule, or it has to also form a big bubble, and then only it can detach from the surface. So until the bubble is detached from the surface, that area is not available for the chemical reaction, charge transfer reaction. So you get a very slow power out of these batteries. So how was this power increased? This power was increased by invention of one molecule or one material which is called manganese dioxide. So what does this material do? So if you replace the copper with manganese dioxide, what happening? Initially, hydrogen was getting converted into H2 gas. This time, when the electron comes, if you see on this side, if you see the electrons, one second. Yeah, if you see those electrons will come and it will reduce the manganese 4 plus to manganese 3 plus. So there will be a charge imbalance in the structure, and it can incorporate one proton inside it. So what will happen if the hydrogen ion is not getting reduced to hydrogen gas? It is as it is, like a proton, just intercalate into the body of MnO2 and get converted to MnOOH. So it is not producing a gas which is an insulator, one. And secondly, your only diffusion of proton is involved. That makes the process very faster. So because of that, you get a very high current of this battery, and this battery are still available in the market by the name alkaline batteries. Okay, so this is how you got to increase the power rate. Now, how to convert these batteries into a secondary batteries? Because all these batteries, what I've told, it's a one-way traffic. I mean, we can only convert the chemical energy to the electrical energy. But if you have excess electrical energy, how to convert it back to chemical energy? People did not come up with that till Nicholson and Carlisle come up with an experiment. So what did they do? So Volta actually did dissimilar metals, so chemical energy, and converted it to produce electricity. So these two persons thought, Nicholson and Carlisle, why not to conduct exactly opposite chemical chain. So they used electrical energy for electrolysis of water and come up with hydrogen and oxygen. And they proved that this electrochemistry is a thermodynamically reversible process, that you can also use electricity to conduct a chemical change. So this experiment was followed by several sort of experiments. So one was Andres Margraf. He electrodeposited zinc from an acidic zinc sulfate solution. And there has been also a report of electrolytic oxidation of manganese 2 plus to manganese 4 plus by Ruteshi. So these two different experiments, but it led to a conclusion that the idea of a reversible cell popped up. So people start thinking that from a same bath, if you can reduce zinc and oxidize Mn2 plus, reduce zinc 2 plus to zinc and oxidize Mn2 plus to 4 plus, then you can actually come up with a reversible cell made out of zinc MnO2. So you don't have to put money on materials every time you use a battery. You just have to fill it with electrical energy and cost will be saved. But they could not do that. Why they could not do that? Because whenever you change Mn2 plus to Mn4 plus, your ionic radius increases, which leads to mechanical strain, which leads to the mechanical failure of the battery. Number two, that neither MnO2 or MnOH, these phases are electronically conductive. And the third in turn, when you try to electrodeposit zinc, it deposits in the form of a dendrites, which shorts the two electrodes, so the battery explodes. So what people understood, though the chemistry is reversible, it is not it is a necessary condition, but not a sufficient condition to run a reversible battery. You need to have mechanical integrity or mechanical reversibility. That is equally important. So that is getting lost with cycles. How this problem was resolved? This was resolved by the invention of these two materials. One is called a nickel electrode. So this is actually, and one is called a metal hydride electrode. So this nickel electrode is actually a combination of nickel hydroxide and nickel oxyhydroxide. So the advantage over MnO2 is this: nickel oxyhydroxide phase is both ionically and electronically conductive. So when you charge that battery, there is no problem for the electron migration at the surface where the charge transfer is going on. So you can have a complete reversibility. And also one point is there, here nickel is converting from 3 plus to 2 plus. So it's not 2 plus to 4 plus. So your ionic radius also does not change. Your volume expansion can be controlled and the battery does not degrade mechanically. Similar happens if you go for metal hydride. So different type of metals are there which actually forms hydride. So this metal can be used as a reservoir of hydrogen, and at a very low potential they can give away hydrogen and they can receive hydrogen. So reversibly, hydrogen can enter those host structures and come out of these host structures. And one of the example is lanthanum nickel. So that is why the first nickel metal hydride battery was built. So you replaced your zinc with that of metal hydride, and you replace your manganese dioxide with nickel oxyhydroxide, which is the nickel electrode. So what you're having during discharge, this metal hydride is delivering, or it is supplying hydrogen or proton, which is actually going through the bath and entering the body of nickel oxyhydroxide, which is getting converted to nickel hydroxides. So you are only having a diffusion of So if you see energy, that is V into Q. If you see the power, that is V into I. So V is the common denomination in all the two parameters. So now people have started targeting V. So how to increase the voltage such that both energy and power can be increased. So they thought, why don't we have the same mechanism, that diffusion of one such ion, but replace hydrogen ion with that of a different ion of a different metal which is much more electropositive. So they came out with lithium. So we are going to have replace hydrogen ion with that of a lithium ion, and it becomes a lithium ion battery. It's as simple as that. It's just a to and fro movement of these lithium ions. And there you have metal hydride. You will have here, you will have metal which can take lithium, or different materials which can incorporate lithium. And also nickel oxyhydroxide can be used as it is, or sometimes most of the times we actually replace it with cobalt oxide. So only problem came because of the voltage. Because if you see the voltage, lithium operates at a voltage of -3, and this nickel oxyhydroxide works, or cobalt oxide works as a voltage of 1.2. So the total voltage of this cell is 4 volt, more than 4 volt, which will give us a higher energy as well as higher power. But that much of volt, your aqueous electrolyte cannot sustain. So they will degrade. So that's why for lithium and battery, we are compelled to take a non-aqueous solutions which can take, or whose electrochemical window is more than 4 volt. Okay. So that leads to the problem of power, because this kind of non-aqueous, what is called electrolytes, do not have that much of conductivity that aqueous solution is to have. And furthermore, they are very volatile and flammable. So that is why all the lithium ion batteries are unsafe, in the sense, if they're exposed to the atmosphere, they will immediately catch fire. It is mostly because of this electrolyte. Okay. But if that is taken care, this system can give us a very high specific energy, that is almost 1.15 kilowatt hour per kg, or 1149 watt hour per kg. But we get a practical energy around 2 to 5 because of other weight coming from other components. So now if my target is gasoline, and if I actually make an actual comparison, so if you take the theoretical capacities, there is a gap of 1:10 or 1:11, if you consider the theoretical capacities. But if you take the practical capacities, we are not even reach 1:10 benchmark. So we are already almost 26 times lesser in terms of battery with respect to gasoline. And if you just take a practical example, suppose an Alto car we will have a liter of 35 liter. So the gasoline weighs 25.9 kg. So you want to replace this gasoline with battery, you need 25.9 multiplied by 26.4 kgs of battery, which is almost 800 kgs of battery, or 750 kgs of battery, which itself sorry, 683 kgs of battery, which itself is 40% of the weight of the car itself. And your total battery energy $132 per kilowatt hour. So in that cost, if you want to replace with this battery, it will cost you 132 multiplied by the kilowatt hour, multiplied by the dollar price. I made it a little earlier. That time it was 73, almost 15 lakh rupees, which is very impractical. You cannot do that. But where you're winning in filling. So one gasoline filling cost about 3710 rupees, and one electricity filling costs around 1230 rupees. So if you think that X time of filling, the cost will be equals, it comes to 510 times filling. So after 510 times filling the entire tank, your cost will be equal. And if you take 7 days per filling, it will give you at least 8 to 9 years. So after 8 to 9 years, your cost will be equal because your installation cost of the batteries are very high. Batteries EV cost very high, and petrol cars cost low. So that is why after running that car for 8 to 9 years, your cost will be equal. And that is why this battery manufacturer or that EV manufacturer are very smart. They used to give you a warranty for 8 years because they know that after 8 years, that batteries won't work. Okay? After that, they won't provide you a warranty. And if you just compare the prices, the Tata Nexon itself costs around 8 lakh, and Tata Nexon EV itself costs around 14 to 15 lakh. So this extra 6 to 7 lakh comes out of the battery. So there is a need for battery materials which can have more power density at a lower price. In fact, 10 years back, your battery price was 1200 kilowatt hour dollar per kilowatt hour, which now come to 132. So we are able to put it down. But how far we can do that? We are able to put it down by smart battery design. But now we have now we have reached some sort of limit. So just by design, we cannot put our battery price down. So now we have to change our battery materials in such a way that it can hold much more energy. So we come with a battery which is best among all the batteries, and that also increased its capacity by almost 100 times in the past 10 years, but still it is confined into portable electronics. Still it is yet to penetrate the EV market because its capacity is not even matching with the gasoline capacity. So we can do two things. Either we can increase the capacity of the anode, or we can increase the capacity of the cathode. Now, the problem with capacity of the cathode is if you increase the capacity of the cathode, your voltage also increases because it's a function of the capacity. If the voltage increases, it makes your electrolyte uncompatible with the cathode, and the battery actually degrades very faster. So it's a risk to come up with a high capacity cathode. Rather than, we can go for a high capacity anode, and my research is on that. So what I did, actually, I replaced our graphite anode with different types of metallic anodes like tin, antimony, lead, bismuth, this kind of anodes. If you see the charge, their gravimetric capacity by weight capacity is almost 3 times than the graphite, if you see tin. And the volumetric capacity is almost 8 to 9 times higher than that of graphite. So I try to replace the graphite anode with that of tin anode. But the problem is you get a volume expansion of in the order of 300%, so 260%. So if you see in this left-hand side, if you start with tin, when it is fully lithiated, the volume grows by 2.6 times and it completely pulverizes. So what are the strategies you can take that you get this capacity but yet save the structure? So we call that some active strategy. That means you don't take one material, you take a combination of two materials. Both of them are active towards lithium. So at different voltage plateau or different voltage potential, they will be expanding. So what the rate of expansion you can resist to some extent. Or you can take another material like copper, which is inactive towards lithium. So what will happen when the tin will take lithium, the copper will come out in the matrix. And what will happen when volume expansion happens, the stress will be taken up by copper. It will plastically deform to take that stress, and your entire structure will be safe from fracture. So these two are called the chemical buffering. Apart from that, you can also have physical buffering by making nanoparticles, nanowire, or you can play with the structure of the current collector also. Okay. So in my study, what I did actually, I combined this active-active, active-inactive strategy and also use a porous current collector. So if you see this is the three strategies I've used. So first one, to take a ternary alloy of tin antimony copper. So what happens? The antimony lithiates first, followed by the lithiation of tin, and in between the copper comes into the matrix and get dispersed. So whatever the volume expansion, it is actually absorbed by this plastic deformation of this copper. And this entire alloy we actually put inside a nickel foam rather than a nickel foil. Okay, what is the advantage? So whatever the expansion happens, that happens inside the foam. So if the material expands, the foam will go under a compressive stress, and these metallic foam are very good in handling compressive stress. So the structure will remain intact. It will not delaminate from the collector. And the third thing what we did, we actually we put the material inside the nickel scaffold and we hit it such that some intermetallic formation also take place, and that will further save the structure from delamination. And we end up with a capacity around 600, 588 after 100 cycle. The cell is still running. So it is almost 2 times than the capacity of graphite, and has been published to this applied surface science. So we are also looking on this on to have more different type of metals and characterize their structures. And this kind of batteries actually we can make in our lab in the form of coin cells, and we are trying to make it in terms of pouch cells and put it to some internal use of IIT itself. So the last thing I want to tell, there's some 3-4 slides remaining. So is lithium and battery is the answer? Okay, so if you see the cost, so in the past 9 to 10 years, the costs have come from 1200 to almost 170 kilowatt hour. But it is nowhere near to the lead acid battery, which is $71 per kilowatt hour. Okay. And if you see the cost bifurcation, the 65% of the cost of lithium and battery is in its raw materials. So that means somehow we can curtail the cost in labor or in utility or indirect cost, but the net raw material cost we are not able to reduce. Right? And that also, these batteries are mostly fabricated in China, where the labor cost is very, very low. You try to make it in Europe or America, your labor cost will be huge. Oh, then you cannot come up with a cost like 176. And also, if you go on to the right hand side, if you see that there is a high cost come from the current collector itself. So you use copper and aluminum as a current collector. There itself 25% of the weight of the battery. So you put a lot of money only for current collectors, which are not even an active part of the battery. And in that sense, if you see the lead acid battery, the 70% comes from lead weight, 14 from water, and 8 from sulfuric acid. All the components of this battery is much, much cheaper than what we have for lead acid battery. This is one. This is concerning the design. Now, if you're concerning the materials, you see the use of lithium. Whatever lithium is extracted, only 1/4 of that comes to battery industry. So I cannot tell the lithium extraction industries to reserve the lithium for batteries. I cannot tell that. So they have to go for other uses in other industries. Similarly, for nickel, only 2% of the nickel which is extracted comes to this lithium and battery chemistry. Whereas if you see lead, 80% of the usage of lead is in the batteries, and lead is the per mass lead is the most recyclable material. Even it is a cottage industry in India. You can even recycle lead at your home. So it is very difficult for this lithium and battery chemistry to challenge a established technology like lead acid battery, particularly in India. It is not possible. But you know that lithium and battery is first superior, but cost-wise, it cannot penetrate the market. So what should be our target? So I got this quote from someone called Donald R. Sadoway. He's a professor in MIT. So he came up with this quote that if you want to make something dirt cheap, make it out of dirt, preferably dirt that is locally sourced.
Professor, sorry to
yeah,
intrude.
so just 2 slides.
Right.
Yeah, so what we are looking for, so rather than imbibing a known technology like the lithium and technology from foreign with limited resources, we should not do that. First, identify your resources which can be scaled at a cheaper price and accordingly develop the technology. That should be our target. So if you see in India, it has 7% of the bauxite reserve, which gives us aluminium. So why don't we plan a battery based on aluminium? And also aluminum is produced already electrolytically. That means that itself is the charging of the battery, plating of aluminum. So that is already industrially established. So why don't come up with an aluminum based battery? And in India, electricity is the cheapest among all the world. So that is why currently we are doing in our lab. So what we did for lithium and battery, the same technology said that lithium will go for mix with tin, make an intermetallic. That same thing will go for aluminum. So aluminum will go and mix with a metal during discharge, and during charge, aluminum plating will take place. And this is how we can actually make an aluminum intermetallic batteries. And we have identified that we are going for an aluminum nickel and aluminum iron system. Now, aluminum iron system will be much cheaper if you can actually pull off these batteries. But we are currently started with aluminum nickel system, which can give us an energy of 546.7 watt hour per kg. Very, very high, almost twice than the commercial lithium and batteries. And these are the final slide. So on the left hand side, what is the current research we are going on? So we're trying to develop an aluminum lithium battery, aluminum nickel battery with non-aqueous solvent. But our future target is to make a battery with molten salt eutectics, which actually will run at a temperature of 100 degrees centigrade. We don't have to put any external heat input here, because the current that will run in the battery will itself generate I square RT heating, which will actually take care of the temperature. But why we are going for molten salt? Because it gives you 10 times more conductivity, and we can actually incorporate it or tag it with the power grids. And this is our ultimate target, that to replace the liquid electrolyte in the aluminum and battery with a solid electrolyte. So then what we have is an aluminum followed by a polymer followed by another metal. So this itself can act as a structural battery. So what you can do, the entire surface of the car you can replace with this battery. So this battery itself is going to be a structural material. You don't have to put any extra battery to run this car. So this is our futuristic goal, and we are going through that. So thank you. I think I'm done. Thank you for giving me this opportunity. Thank you.